So the first speaker of the program is Professor Misha Belkin. So now I'll talk, hopefully not too long about him, but so Professor Belkin is a renowned researcher in theoretical machine learning and data analysis. He's currently professor at the Ali Choglu Data Science Institute at UC San Diego, and he was at Ohio State before joining UCSD. He received his PhD in 2003 from the Department of Mathematics at U of Chicago under late partner Nyoji. Maybe he was his first student, I'm not sure, he'll tell us. His thesis was on problems of learning on manifolds. And, you know, for those of you which are in the audience which care about analysis, Chicago is not only famous about, it's famous about many things, and not only about the School of Economics, but it's a great school of mathematical analysis there, and a great school in statistics and machine learning as well. So some of Professor Belkin's most famous results come from his PhD thesis and his earlier work on differential geometric methods on data analysis, in particular Laplacian eigenmaps, graph regularizations, manifold regularizations, and so on. And most recently, he has been interested in most fundamental principles of machine learning research. In particular, I would say generalization, convexity, and non-convexity issues, overfitting, and so on, interpolation. And one of his key recent findings is, you know, some of you have seen this double descent risk curve, which is in contrast with the, you know, most commonly taught U-shaped curve in classroom environments. So Professor Belkin received the NSF Career Award, number of Best Papers Awards. He has co-chaired COLT last year. He is a PI in the collaboration on the Theoretical Foundation of Deep Learning from NSF and Simons Foundations. He has been on many editorial boards of fundamental, most important journals in machine learning, Journal of Machine Learning Research, IEEE Paternizing Machine Learning, Machine Intelligence, CM Journal of Mathematics of Data Science, and we can talk forever. So I think I've stolen enough of Professor Belkin's time. So let's thank him for his presence at Science Week.
Thank you very much, Alessandro. Thank you for inviting me. It's great to be here. Well, alas, only virtually. Yeah, so I would like to sort of today to discuss some of the recent progress in the last maybe few years that we have done toward, you know, understanding of deep learning and understanding what's going on with this. Oops, sorry, what's going on with my PowerPoint? Okay, here it's working. So you know, we have seen neural networks have become such a big part of machine learning in recent years. And when you look at the architectures of those objects, you realize that these are kind of mathematical models which are extraordinarily complicated, kind of almost sort of baroque in their detail. And it is not completely clear why they're so complicated and what is the underlying principles and what we sort of, how should we understand the subject. And I would like to point out that in some sense, science and engineering have slightly different sort of motives. Because when we're acting as engineers, right, we would like our sort of first priorities to improve performance. And improving performance usually means building on something which is already there. And that leads to the structures becoming even more complicated, right? You build on what exists. When you do science, right, you kind of go in the opposite direction. You want to strip unnecessary parts and understand what is a fundamental object there. So sort of, I've been trying to sort of working on trying to understand some of the fundamentals, sort of trying to approach it from the point of view of not necessarily getting, you know, state-of-the-art performance, but trying to understand what happens in the systems. And the sort of remarkable thing which happened in recent years, there was a crisis of machine learning theory. And sort of on one hand side, there was a kind of argument that machine learning has become alchemy, and in the sense that not necessarily alchemy is bad as such. So it's more that a kind of pre-scientific pursuit, right? When you didn't have it's pre-scientific chemistry essentially, when we didn't have, well, the humanity didn't have clear understanding of chemical properties of models. And so machine learning is a little bit like that, because we don't know, like there are lots and lots of parameters and we don't know what are the principles. How do we choose architectures? How do we choose parameters? And so on. But the kind of counterpoint to this was, and this is from, the top one is from Rahim Indirect, and Ali Rahimi gave a very nice talk at NIPS in 2017. The kind of counterpoint to this was a point by Yann LeCun, and he said that basically machine learning theory looking for lost keys on the lamppost because that's where the light is. So there is I don't know if you can see it, but there is a kind of cartoon of a drunk person looking for lost keys under the light. Right? So somehow the idea is that theory of machine learning is not really explaining what it needs to explain, right? It's looking under the light because that's what we know how to analyze. But it's not actually finding the keys there because the keys are probably not under the lamppost. I mean, fundamentally, I think that both of these are valid points. But I would like to sort of say that theory doesn't have to be attached to a lamp, right? Perhaps more useful as a flashlight that you can take with you, a floodlight that you can turn around and, look for the keys where, you think they are. Okay, so now this is what are some of the key questions? Why was there this crisis? What was so difficult? And I think we should separate two things. One is optimization, and the basic question there, why can non-convex objective functions be optimized? Because sort of traditionally we believe that convexity is necessary. Okay, I shouldn't say necessary, but sort of non-convex functions generically were considered to be impossible. So non-convex analysis usually deals with some very specific things. So why is it that we can optimize these neural networks? And the second question is generalization. Why do neural networks generalize to unseen data? And finally, the role of depth. Why do deep neural networks work better? So I think the first question is the one for which actually we have a very good answer, and I think we do understand optimization much, much better today. The second question, I think we have some partial results for that, and we have a better understanding of what the issue is, but we are not yet there. And today I will particularly discuss the second question, actually, and I'll describe some of the progress related to interpolation and the double descent curve. And at the end, I'll very briefly mention optimization. Okay, so let's sort of start. And I should say that I wrote a kind of review paper which describes much of what I'm talking about that appeared in Acton America last year. And basically, the idea that overparameterization and interpolation gives us a lot of answers. Not answers, but insights into these questions. I should not say answers. Oh, by the way, do feel free to interrupt me with questions if they're ready. I'm more than happy to slow down and answer anything. Do not hesitate. Okay, so now let's do a setup. And then, so my first sort of part of this talk, I would like to discuss what exactly is the issue? Why is there a crisis? What's the nature of this crisis? And for that, I need to describe this kind of traditional view on machine learning, U-shaped curve bias variance trade-off and so on. So let me start with this, and then I point out like what is problematic about it and why we need something different. So, okay, sorry. So the setup, we have data, xi, yi. Xi's are features in RD, and yi's are labels. For simplicity, we can just think of minus 1 and 1. A two-class problem, of course, they can be different things like real numbers or can be multi-class and so on. In any case, the goal of machine learning is to construct a function, RD to R, that best generalizes to new data given the training data, right? So look at the training data, analyze it, and construct this new function. And if you have seen some sort of basic machine learning, then what is the best predictor? Well, under the standard statistical assumptions, which in this case would be IID, so I'm assuming that my data are independent, identically distributed, then the best predictor is a predictor which minimizes a certain loss. So for regression, this would be square loss. For classification, usually the binary loss, and that's the best. Now, how do we actually operate in machine learning? Well, the typical algorithm here is something called empirical risk minimization, right? And how does it work? We take a class of functions, H, and from this class, we choose by some algorithm, usually stochastic gradient descent or some such, we choose a function which minimizes the empirical loss. So we attempt to choose, we don't always succeed. So this is minimizes the empirical risk, the training loss, over a class of functions H. Now, one of the key issues here is how to choose this H, right? What is my class of functions? And the way to think about it is class of functions corresponds to model complexity, right? And the easiest way to think about it is just number of parameters. And the classical view on this is the following. If the number of parameters is small, we get underfitting, right? Because my model is not powerful enough to actually adequately describe the data. When the number of parameters is high, we get overfitting. So I can describe, so it's somewhere here, I can describe the number of parameters, I can describe the training sample really well, but I'm somehow fitting my model to idiosyncratic aspects of the data, and that doesn't work. That's definitely the good predictions. And the goal in this setup is to actually find what you would call the sweet spot, which is the point in the middle. And that somehow is, optimal. So this is a traditional view, and probably it's very commonly presented in books and so on. So a kind of corollary of that is that a model with zero training error is overfit to the training data and will generalize poorly, right? Because the model with zero training data is somewhere here on the very right of this graph. So now this is the traditional thinking about this. And the analysis which follows from that is something like this. So let me very briefly outline this kind of theory of learning. And the idea is the following. So I have the goal of machine learning, which is F star, right? And that is the minimum of unseen data. And I have goal of empirical risk minimization. I'll call it F star ARM. And that is the minimum of the data which we have seen, right? That's the difference, right? One is unseen, the other is seen. And we would like to somehow connect it. What would we like? And this is really any analysis must do something like this. We want to say that F star ARM, which is what we get, which is what we see, which is what we, get in practice, is not too far from F star, which is, the future performance. So you know, on like financial document, they always say, like mutual funds and so on, they always say past returns are not indicative of future performance. And this, of course, is nonsense because, we don't have any better prediction of future performance than past returns. There is nothing. It's not a perfect predictor, of course, but there is nothing better. Okay, so now if you go back to Vapnik theory, so if you go forward to Vapnik theory, so Vapnik has this very nice book that he posits that the theory of induction, what we call machine learning, is based on the uniform law of large numbers, and effective methods of inference must include capacity control. So let me unpack this a bit, and let me start with uniform law of large numbers. So uniform law of large numbers simply means that empirical laws for any f in my function class approximate the expected loss. That meaning that what we see, right, with my data is what we get in the future. And finally, the capacity control, not finally, but secondly, the capacity control is saying that H, my hypothesis class, contains functions that approximate f star. Because if my hypothesis class doesn't contain any functions close to the real optimum, then what am I doing? It's useless, right? I'm dead. So that's basically what we have. And if we have 1 plus 2, then we can actually claim that f star and f star ARM are approximately the same. Their performance is approximately the same. So this is empirical risk minimization. Well, really empirical and structural risk minimization, according to Vapnik. And the kind of bound that you get from this, and these are like lots and lots of classical bounds, these are WYSIWYG bounds. What you see is what you get. Probably hundreds of different, maybe even thousands of different bounds on this form. So what you have is that on the left, you have this expected risk, which is what you get. And on the right, you have empirical risk, which is what you see on your data. So the left-hand side, you don't see, you will get it in the future. But the right hand is what you see, plus some sort of model complexity term. And the model complexity term basically is usually something like square root of the VC dimension or the number of parameters depending by the number of data points. So this is a classical bound, okay? And now I would like to discuss what the issue with this analysis and where the crisis of machine learning coming from. So let me skip this. And the question is really very simple. And the question is, well, remember that there was this quote before that said that zero loss overfits, okay? And I will call zero loss interpolation because you know, if you think what interpolation is mathematically, it is actually zero loss. It's exactly that. So let's look at this experiment, which is, I think, a really interesting set of experiments from Zhang et al., an influential paper. So what they did, they took a neural net and they trained it on CIFAR10, which is a vision data set, to get 100% training accuracy. And you would think that 100% training accuracy overfits. Well, should overfit the data, right? According to this kind of classical view, there is, you get perfect accuracy. But what we see is that this actually not quite so. If the test accuracy is not bad at all. In fact, it's not that far from, the best you could get. It's almost 90%. So if there is any overfitting, it is not significant. So that's pretty remarkable. And then, of course, you realize that something like that was actually noticed much earlier, even before the modern age of neural networks. And in fact, it was kind of the premise of this paper by Shapiro, Freund, Bartlett, and Lee, which actually, the abstract said that one of the surprising phenomena observed in experiments with boosting is that test error of the generated hypothesis does not increase as its size becomes very large, and often is observed to decrease even after the training error reaches zero. So that's pretty remarkable, right? So you reach zero, you think, okay, you're overfitting, but no, you can actually continue training and you don't, apparently, are not overfitting. So what's going on? And that was actually kind of a big deal at that point. And this paper in particular introduced this margin bounds, which were quite influential. So let me first point out that this is suggestive, but doesn't directly invalidate WYSIWYG bounds. And let me give a kind of more direct way to test model complexity. And I see there is a question. Please go ahead.
Yes. Well, I have a question. I don't know if anybody else in the audience, but myself. So when you reach the zero training error, then how do you proceed? Like, because to me it seems that, yeah, please.
Oh, because it's a classification error, right? It's not, you can, so imagine I'm doing regression, even when I have classification error zero, right? It doesn't mean that regression error is zero, so I can proceed. So you could keep doing boosting in particular.
So you keep going with the same exact strategy that you had started with.
Exactly. Think about training. Suppose I'm doing regression, right? But I'm measuring accuracy in terms of classification. Even if I hit classification error zero, my regression error is still not zero, and I still continue my gradient descent. Boosting doesn't do that, of course, exactly, but it's kind of a similar thing.
So the reason for which I'm asking is that if I'm already interpolating, right, and I'm interpolating in a way, I can never be at that point sure that interpolating a different way is better, because my criteria is basically the same criterion. So I have many solutions. I reach many different solutions of the same problem. But when I stop there, then I don't. When do I stop? That's what I'm basically the question, right?
Yeah. So there are really two questions here. One is that. Okay, let me point out that I'm losing interpolation slightly loosely. I'm saying loss equals zero, but I'm not saying which loss. Right. So I think true interpolation, where the square loss is equal to zero, that's like what with mathematics called interpolation. I'm here using a classification interpolation, so the classification loss equals to zero, meaning that the loss is actually, the sign of the prediction function is correct. And that's a weaker condition. So I can continue training when that happens because my square loss is not zero, some other loss is not zero still. So I'm conflating those two, but I'll get to the actual exact interpolation in a minute. I'm sort of semi-intentionally conflating them. So let me get to the actual mathematical strict interpolation in terms of the square loss. So how would you test model complexity? Okay, so how would you test whether WYSIWYG bound is okay? And the simplest thing, probably the simplest setup, is to add label noise. Okay, and what do I mean by label noise? Well, suppose I have two classes, and imagine they're just linearly separable. Okay, then this is optimal predictor. You could kind of imagine red cluster and blue clusters are Gaussians. Okay, and they're just samples from them. Now, and they're separated, so there is not much intersection, or no intersection at all. Now, what I'm going to do, I'm going to flip some of the labels at random. So I'm just going to take 20% of the labels and just flip them. Now, of course, these are not linearly separable. And if you think about it, you realize that the previous boundary is still optimal. Because for points which are not flipped, it's optimal, and for points which are flipped, you don't know which one, so it's equally. So the optimal boundary actually didn't change; it's still this line. But if suppose now I would like to do some sort of interpolation, then this is becoming tricky because to get zero loss, I need a boundary which kind of goes I don't know, it's something pretty crazy. Okay, I'm doing a terrible job, but you can see the problem, right? Because if I want to interpolate, I have to have a boundary which kind of goes around this noisy points. And the complexity of that is going to be awful. So it looks like, okay, this is clearly overfitting, right? I am doing terribly. And so model complexity, so what do you expect? You expect overfitting to become very severe as model complexity grows, because you really would like to separate them with a linear function, but instead you're going some sort of crazy separating curve. But let's see what happens in real sort of examples. And this is actually from our paper with my students, my former students, Sivan Ma and Sumik Mantal. And let's look at the following. So this is MNIST. So it's a 10 class data set with handwritten digits. And on the x-axis, I will have label noise, which is just, so I'm taking the label, and there are 10 possible labels. And for 20, 30, 40, and so on % of the training and test data, I'm just flipping them at random. So I'll just take any label. And on the x-axis, so that's the x-axis is the level of noise. The y-axis is the test classification error. Okay? So this is classification error, not accuracy. It's the other way around. And you realize that when there is no noise, it's almost separable, right? Because my error is close to 0. It's like 2% or something like that. Now, when I'm increasing the amount of noise, of course, when there is 100% noise, my error is going to be 90%, right? Why not 100? Because by accident, sometimes you get 1/10 of the time, you get the right class just by accident. And then you realize that the best optimal, the base optimal, is actually this green line. It linearly connects 0 to 100, right? Nothing can, to like at 100 it's 90, and at 0 it's 0, right? Nothing can possibly beat that, because that's how the problem is set up. This is the best possible. Now, what is the red line? So there are a bunch of other lines like neural networks and so on, but let's just concentrate on the red line. Red line is something called Laplace kernel machine, and if you're not familiar with kernel machine, it doesn't really matter exactly how it works. What is important, it's a predictor, and it is trained to have exactly 0 loss on my data in terms of the square loss. And that is done because training Laplace kernel is just matrix inversion, and that I can do mathematically exact. When I say exact, of course, it's up to numerical precision, something like 10 to the minus 25. Nothing is literally exact in a machine. No real numbers. But this is 10 to the minus 25 accuracy. So here is what you observe. You observe that as the amount of label noise increases, right, as I flip more and more of my points, the red line, of course, gets worse, but it tracks the green line actually very closely. And even for something like 60% label noise, it's still quite good, right? It's only maybe 5% worse than the best possible. And this is kind of crazy, because if you think about what's happening there, right? 60% of my data have no information at all. It's pure noise. And I'm fitting all of that exactly. So I'm like overfitting terribly to noise in principle. I'm overfitting terribly. And yet I'm paying only like a few % price for that over the best possible, theoretically best possible, which is a green line. Okay, any questions about this? Because I think this is kind of maybe the sort of most distilled observation of this. Interpolation doesn't really overfit, even for very noisy data.
Questions? So my question here is, does the amount of data that you have matter for this? Like, if you have very few data, does it behave in a similar way as if you have a lot of data? Because what I'm thinking is, okay, good.
This is pretty stable with respect to the data. it doesn't seem like there is a big difference.
So my thought is this one, right? So if you have, let's say that I have all the elements of the population, then, you know, even if you interpolate, it's fine, no matter what, because, you know, you have all the elements of the population. But suppose I have very few elements of the population. So suppose I have almost all the elements of the population. Then if I interpolate, I almost do always right, because anyways, what I haven't seen is very little. Well, if I have very few data with respect to the full population, then maybe I'm in more troubles, because there is a lot that I'm missing. So where is this intuition not valid?
No, even when you have almost full population, right? Imagine you have very dense cover of your population. Interpolation is not that good, right? Because you are fitting all the noise. You want to average it, but you're actually fitting it. Like you are going to get some sort of, you know, you're going to get something like this, right? So even full population doesn't help you here.
Got it.
In principle, you can be in trouble even if you have like essentially all data.
Got it.
So it's pretty striking, because it really contradicts, I think, this kind of our idea that fitting noise is bad. And let me explain this a little bit more in terms of this uniform bounds, because that, I think, is kind of a manifestation of this crisis. Suppose I would like this uniform bounds like this bounds, the Wysiwyk bounds, account for this, right? What do I have? My expected loss is not equal to 0, right? Because even the best predictor cannot deal with noise, right? The noise is somehow like, it's a price we have to pay. Even the optimal predictor cannot do better than the noise level. So the test loss is never going to be 0. The training loss, however, is 0, right? So this complexity term must account directly for the test loss for this bound to make any sense. And is it possible? Well, not really, because let's think what happens. Let's take some high level of noise and let's see what this must account for, right? So it better be, so whatever bound I have, it better be bigger than 0.7, because 0.7 is my noise level, and that's what the optimal predictor does. So if my bound is below 0.7, then I'm wrong. It just cannot be true. On the other hand, if I just predict my data at random, I get 0.9, right? Because 90% is error of random predictor. So if I'm over 0.9, I'm useless. So this is basically what it is. To be useful, it must be smaller than 0.9. To be correct, it must be bigger than 0.7. Now, if you think about it, well, it's really difficult for this bound to be in this range, because, you know, O hides constant, right? And furthermore, it has like log factors and other stuff. And you see, this is like super tight range. Even a constant factor of 2 would kill it, right? You cannot be a factor of 2 off. You're out of this range. So there are really no, maybe I shouldn't say no, but essentially no bounds like that. And furthermore, it's not clear how would it know this bound, this 0.7 to 0.9 range. So there have been some recent work by, in particular by Nagarajan and Colte and Bartlett and Long, who showed that in some settings, having a bound like that is not possible. So now, okay, you can say, well, okay, this is kind of weird, but why is this a crisis? And the reason it's a crisis, I mean, one of the reasons it's a crisis, it contradicts this kind of accepted statistical wisdom. On the other hand, arguably, this is very close to best practice for deep learning. So it's not some sort of weird, you know, aberration that we can ignore and, you know, sweep somewhere in the corner. It's actually something quite fundamental. I really like this quote from Ruslan's tutorial a few years ago. He said, the best way to solve the problem, you build a very big system, and you want to hit 0 training error. So it's not like you don't necessarily stop at 0 training error. You want to probably like do some other things to get state of the art. But even if you just do that, you already get results which are non-trivial, which are okay. Now, furthermore, if you have, like the size of these models has been growing, and just, in 2017, the biggest models, so the models here are circles, and the area of the circles corresponds to the number of parameters. So in 2017, the biggest models were about 150 million parameters. And in particular, the model that I showed you first is actually kind of small. It only has about 6 million parameters. Now, in 2020, GPT-3 has already 175 billion parameters, right? This is to scale. And of course, now there are models with over 1 trillion parameters. And yeah, you can look for those models that we discussed before here. So, the size of these models have really mushroomed just in the last few years, in the last 5 years or so. In fact, it's been growing definitely faster than the Moore's law. So what's going on? And I should point out, it's kind of interesting because it's upsets. So Yann LeCun, for example, on many occasions said something like this, like deep learning breaks some basic rules of statistics. In fact, it was recognized actually quite a few years ago. In '95, Leo Breiman, famous statistician, he wrote this nice note, Reflections After Referring Papers for NIPS, and he asked several questions, and in particular, why don't heavily parameterized neural networks overfit the data? So clearly, this has been around, but somehow I guess at that time it didn't. Guess it wasn't such a pressing issue as it is now. Okay, so let me summarize empirical finding, and then I'll try to sort of give a very brief. So this is why things sort of are strange. But now, what is the way forward? And first, what is the empirical finding? Is that empirical finding is goal of optimization, interpolation, and minimizing empirical loss. Quite unexpectedly, at least from a classical point of view, aligns with the goal of machine learning, which is minimizing the expected loss. So that's the finding. Now, a kind of corollary of that is that new theory of induction, something we would like to have, cannot be based on what Wapnick suggested, on uniform loss of large numbers with capacity control. So we need something else. And we do have something which is quite different. And I invite you to think about one nearest neighbor predictor, right? So you just have a bunch of points, you take one which is closest, right? You say, okay, this is my data point. And this is really suggestive in the following sense, that it's an interpolating classifier. It clearly interpolates, right? Because the point is its own nearest neighbor, so the label is always the same. And it does have a sharp performance guarantee. It's bounded by twice the base risk, which is a classical result. And it's not really explained by empirical risk minimization. So it turns out that you can actually do much better than that. And in fact, there are schemes which I don't really have to try to describe it, but they're kind of like nearest neighbor schemes. But they are what you may call Shepard's interpolation or interpolated K-NIN schemes, which give curves like this. So let me just maybe concentrate on this picture on the right, and let's ignore the theory. I should say the first result of this fork was by Devroy, Gurf, and Kurzak for 98, and then we showed optimality with Daniel Su and Partha Mitra, and follow up by Sasha Raklin and Sasha Tsibakov. So what is the picture? The picture is the following. So I think seeing the picture is enough. So the true predictor here is y equals x. And the data is sampled from y equals x plus noise, right? So if the best predictor possible here is this blue line. Now the data, of course, are noisy, right? So none of the data are exactly on the blue line. So a priori, if I know what's best, I would choose a blue line. Alternatively, I could do linear regression and also figure out something like this blue line, right? Linear regression would probably work quite fine here. And the weird thing is that one of these schemes, interpolating schemes, produces this red curve. And you can see this red curve, it has this kind of little antennas, like somebody said, like snail antennas or something. They are kind of, at every data point, it's not actually close to the blue line. But yet, if you look at an average point here, it's not that far from the blue line, right? Somehow, on average, you're almost at the blue line. So, and what can be proved about this, it looks pretty crazy, but what can be proved is that this is actually in some sense optimal in minimax, statistical minimax sense. And that's weird, right? Because you really wouldn't expect this to be the case. Oops, sorry. So that's a kind of counterintuitive, because you think, like, if you just look at it, right, this is terrible. Okay, so this basically shows that interpolating methods can be optimal. But let me now sort of make the connections to neural networks. Any questions about this? Questions, comments?
Questions also from the audience, from the online audience? No.
Okay, let me then go ahead. So maybe I'll skip this one, but so basically what we have shown that interpolation empirically aligns with generalization. Theory of interpolation cannot be based on uniform bound. And I showed that at least some interpolating methods have statistical validity. But there is a mismatch because we are not analyzing complexity control, right? We want to have something like neural networks, not like nearest neighbors, even though they share the abbreviation. So key question for new theory is dependence on generalization on model complexity. And here I would like to discuss double descent, which is really kind of sort of a cartoon which outlines a way forward for this, like what's happening. So let's briefly revisit this classical picture. You have this U-shaped curve, and as you increase in complexity, right, as you're increasing the number of parameters, you go from underfitting to overfitting, and the goal is to find some sort of sweet spot. But what if you go past overfitting, right? So when does overfitting end? Well, classically, when you have zero loss in terms of regression, right? Because there is nothing else to do. But notice that with a linear, with a model like a neural network, you can have arbitrary model, right? And train it on any data. So nothing prevents you from training a model whose number of parameters is much larger than the number of data points. And when you do this, you realize something quite remarkable, is that as you increase the number of parameters past this interpolation threshold, so interpolation threshold is when you fit the data exactly, and by fitting I mean in regression sense, you go into this kind of modern interpolating regime. And in this regime, as you increase the number of parameters, what typically happens is that the test loss, our risk, goes down. So we call it double descent. This was with Daniel Su C1 minus cubic bundle. We call it double descent because there is a kind of this classical descent when the curve goes down with increasing of parameter, then it goes up, and then there is a second descent beyond the interpolation threshold. And the remarkable thing is that very complex model with huge numbers of parameters can actually outperform classical models. So in some sense, this is kind of a summary of empirical sort of distillation of empirical observation, but it actually gives a way toward analyzing this phenomenon. And I should point out it's been observed in all sorts of different models. Maybe I'll skip this. But let me give you sort of one maybe a very simple way to think about it. Let's think about random ReLU networks. Okay, random ReLU networks is simply a network of this form. Okay, and I am choosing B, J, and CJ at random, and alpha J I'm training. So it's a particularly simple neural network. You can think of it's some sort of random feature model if you want. And I'm training this by linear regression. So let's see what happens. When I only have 3 neurons, then so this red circles are data points. There's like 11 data points, I think. With 3 neurons, I get this kind of piecewise linear, and these are ReLUs, right? So these are piecewise linear functions. So I'm going to get this piecewise linear, which seems to be a pretty good fit to my data. When I increase the number of neurons to 30 neurons, I see that this is overfitting, right? I'm clearly overfitting. It goes up and down, kind of oscillates. Doesn't look like there is a lot of information there. But when I increase the number of neurons even further, I get something pretty remarkable. I get this nice smooth curve, which goes through the data. And notice actually that this curve is still piecewise linear, but you cannot see linear pieces because I have 3,000 neurons and the pieces are too tiny to be seen. They're like smaller than a pixel probably on my screen. So you can kind of see that this is essentially on the left, this model is kind of parametric and this is sort of non-parametric. And they're both sort of reasonable, but the model in the middle is not a good model. It's clear overfitting. So you can see that overfitting happens in the middle between parametric and non-parametric. And I'm running out of time, so I'll skip that. So there have been quite a lot of work in this direction, and including some of our work. One interesting finding was that deep neural ReLU network are actually in some settings equivalent to Laplace kernels. And so we are now getting descriptions of some of these objects. And this actually relates to this neural tangent kernel discovery. Okay, so maybe I'll make a couple of comments about this, and then I'll say like a few words about optimization, and I'll stop. So first, ARM and interpolation. So let me point out that for linear one, so this is kind of, imagine I'm just doing classical linear regression, right? And I'm simply minimizing, though, this would be just a square loss, f of xi minus yi squared, right? And just minimizing that as a classical linear regression. And this modern setting is something else, like I'm fitting my data exactly, and I'm minimizing the norm, which is also linear regression, but it's you're using pseudo-inverse. And classically, you wouldn't use pseudo-inverse, you would actually like normally regularize it. But what this is saying is that essentially in many cases you can skip regularization, you just invert, and it works fine. And interestingly enough, if you use something like stochastic gradient or gradient descent, you would not actually, like, you don't even have to know which regime I'm in. You don't have, it will converge to the minimum norm solution in the modern case to this one and to the, that one in the classical case. So, yeah. Okay, so maybe I'll summarize here and say like a couple of words about optimization. And so what is the framework for modern machine learning? You could kind of think what suggesting is that this is Occam's razor based on inductive bias. So you want to have kind of a smooth function subject to interpolating the data. And there are in some sense, so among the functions in your function class, you want to choose somehow the nicest such that it interpolates the data. And there are different ways to interpolate. You can find some sort of minimum functional norm solutions. You can do some sort of implicit optimization, stochastic gradient descent, or you can do averaging, and they all have kind of similar effect. And in fact, all coincides for kernel machines, so there is something special for them. So that's a summary. So what is remarkable, what you observe, is that it somehow gives you this new view of overfitting. And on the left, you have this classical regime. On the right, you have this modern regime, and overfitting is this band in the middle. And you can deal with this differently. You can kind of regularize if you have some predictor here, and regularizing kind of takes you to this classical regime, or you can simply add more parameters and go to the modern regime. So just add more parameters, and that essentially does something very similar to regularization. So yeah, so overfitting doesn't really relate to your loss. Overfitting somehow is how should I say it? It's somehow a fairly subtle interaction between data and the model. Okay, so that's generalization. And now, as promised, I'll say a few words about optimization. And maybe I'll just have like really just one slide. So one slide, if really, like if you think about non-convex optimization, we think about something like I have here, right? And this is awful because, well, gradient descent can find a local minimum for sure, but it probably will never find a global minimum. Just a lot of local minima to worry about. And from this point of view, it's not clear how training neural networks can be possible at all because they're clearly very non-convex. However, this is kind of this classical landscape. But when you're over-parameterized, when the number of parameters is larger than the number of data points, this is really not what happens. And a better picture is something like this. And this is from our paper with Jerry Liu and Libin Zhu, my students. And what you see here is that you have this valley of global minima. There are many of them. There is a whole lot of global minima. And now, if you think here what gradient descent does, right? It's like taking a ball and kind of rolling it downhill. And when it rolls downhill, it actually rolls down to the bottom of the valley very easily. So even this landscape is highly non-convex. In fact, it's not even convex locally. It's not really a problem because gradient descent will happily converge to a global minimum. So that's optimization. So somehow having more parameters in optimization makes the problem easier. Okay, I'll stop here. And let me just maybe point out some missing pieces. So that's what we understand. So optimization we understand quite well. However, we're not yet there with with full understanding of generalization. And here are some missing pieces. And the first piece is like, why are deep neural networks better than one nearest neighbor? It's not completely clear. 2, why does optimizing neural networks find reasonable solutions? In some sense, optimization is easy. Generalization seems much trickier, at least at this point. And finally, what is the role of depth? So far, I haven't said anything about deep neural networks, but in practice, they're often quite deep. We have some understanding of it, but it's still rather lacking at this point, I feel. And I'll stop here. Thank you.
Yes, let's thank Dr. Belkin for the great talk. So Questions or comments? Voilà. I can start.
Hi.
Oh, yeah, please. Yes.
I don't know if you can hear me. Thank you.
Yes.
Thank you very much for the talk. I was wondering what's your opinion on this kind of silly setup when the data have random labels. So we don't add, some additional noise, but we just randomly assign ones or zeros to our data points. And then even, our network will probably interpolate, but the generalization error will still be close to 1/2. What are your thoughts on that?
Could you repeat? So you are randomizing some of the labels, and then
Yeah. So this kind of silly setup when you're randomizing basically all of the labels. So basically, your bias error is half, 0.5. You have no chance of learning anything because there is no structure.
Right.
But if you fit, if you have a large enough neural network, it will memorize the data and have zero error, training error.
For sure, yeah, you can fit the data with a neural network, but of course there will be no generalization out of your data random.
No generalization.
So it's not too hard to prove that you can fit it using, if your neural network is big enough, you can actually prove that you will fit the data. But you are probably not learning any structure. I mean, how can you learn any structure, right, if it's completely random?
Yeah. So have you considered maybe that, some structure of the data is good for the neural networks to learn? And maybe that's the reason for double descent?
Double descent doesn't directly okay, yes. So yeah, it is true that in some sense, this is, I think, a very valid point. So double descent, right? In this, though, if you look somewhere here, right, when the number of parameters is huge, you have to know something about your data because there are lots and lots of different solutions. And they cannot all be good, right? There are lots of bad solutions as well as probably some good ones. So the kind of explanation that we have for this is that essentially it's looking for something like solutions with a small norm. And if you somehow have some sort of reasonable structure on the data, then small norm solutions are usually good, right? It's roughly what linear regression does. Now, in some special cases, you can prove that small norm solutions are actually good for certain linear regression setups. In this very general settings, it's hard to prove things, but sort of intuitively, something like that must be happening, or at least we believe it's happening.
I see. And I have one additional question. The double descent curve, does it depend on the optimization? Does it have to be SGD model, or can it be something else? Have you?
It doesn't have to be specifically SGD. Yeah, it will work with all the standard, optimization methods. You can certainly have some crazy method, right? If you do something really crazy, you can sort of make sure that here you can find this really terrible model, right? That you are at the noise level. So you certainly can sort of concoct like really bad optimization methods. But I think with all the practical ones, it happens. Well, I don't know all. It seems to be happening consistently. That's, yeah.
I see. Okay, thank you very much. Thank you for a great talk.
Sure, thank you.
Other questions? So I have one. So, well, actually, I had already a couple, so I have a third one. So the question is, so I'm trying to understand a little bit where could the benefit of over-parameterization comes from. So now what I'm thinking, my intuition tells me this. Let's say that I have a one-dimensional, curve with a lot of peaks around, one close to the other. Now, if the peak is very tall, then it's kind of a lot of work to go around that peak. Okay. Well, if I have an extra dimension, I can like go around that peak. If this peak is very steep, but it has so it might be that it's convenient to go around the peak instead of going over the peak. So this is intuition number one. Intuition number two is like if I increase the dimensions, naturally I create distance between points. So automatically between these two together, somehow I create space for going around peaks which cover up the global minima. So is there any value in this intuition?
Yeah, I think that peak intuition is actually very nice. It's so what you see in Heidelberg. So in fact, let me just go to this picture because I think this is
Because those are very high peaks and they are clustered together. So you have to figure it out how to create distance so you can pass through those peaks, right? So that's how I see that.
I would think about it slightly different. Like here, you see, like I'm fitting the data with peaks, right?
Right.
It's very peaky. And in one dimension, these peaks kind of crowd each other.
Right.
But in high dimension, there is actually more space.
Right.
And even though you have these peaks, it is somehow okay because there is like lots and lots of space in high dimension, right? So they basically don't bother you at all. So in one dimension, it's even though it's asymptotically optimal, but it's somehow the constants are going to be terrible. It's just going to be pain to use. But in high dimension, it's really not an issue. It's not quite what you asked, but I think it's a very similar intuition. Is that these peaks somehow in high dimension, there is lots of space to go around the peaks.
Right.
And even though you have many peaks, it's okay somehow.
Right. So there are peaks which are high, so you can go around easier with extra dimension. And when you increase dimension, you create space. And so
you create space.
You create space. And so even simple algorithms have some sort of easier way to get through this local minimum and explore it with more the landscape.
Exactly. Yeah. Somehow exploration is easy in high dimension. So
Right.
Somehow you transition from something like this. Too many slides. Sorry. Like you transition from something on the left, right? By adding a few dimensions, it becomes on the right. Because if you have three equations and one variables, right, you're going to get some crazy complicated landscape. But if you have three equations in 10 variables, right, suddenly you have like tons of solutions. It's very easy to find them. Why they're good is a different issue, why the solutions are good, but certainly much easier to find the solution.
And then you can have also many solutions, right? So you have many different solutions to the problem, because you might have different possibilities to go through this local minimum and reach like a good point, like an optimum or something.
Exactly. Yeah.
Good. Other questions? Well, we have already kept Dr. Belkin 6 minutes over time, so let's thank him for the great talk and for all the insights he gave us today. So,
thank you very much.
Yeah, so I refer everybody to the Slack chat and the website for tomorrow's events, and then we are going to have many others. So thank you very much for everybody for your attendance today. Okay, thank you.